I'm going to start by drawing a solenoidal system similar to what we had in our last class meeting. Over here on the left-hand side, and then over here on the right, I'm going to draw a squarish thing. Like so. So I have two different types of cores here, not particularly important other than when we start talking about a couple of other quantities here. So for this cylindrical core on the left-hand side, I'm going to wrap a wire around the top part of the core like so, forming a coil with N1 turns. And I'm going to arbitrarily say that my current I1 of T is flowing down it in this direction, and my induced voltage drop of V1 of T will be across like so. And then I'm going to put a second coil I'm going to wrap it around it in this way. This second coil has N2 turns, current of I2 is leaving, and here's our induced voltage drop of V2. And I can do something similar for this core over here on the right as well. So I might put a coil on this leg of the structure. Where I might have N1 turns over here. And similarly, I might have a coil on this leg of the structure. We'll call that N2 turns, current I2 flowing out. Here's my voltage V2. All right, so effectively structures like these exists when we want to force or ensure that our system has magnetic coupling between our coils. These type of structures are very commonly called transformers. So the degree by which the coils are coupled is usually characterized by what's called the coupling coefficient K. Okay, so K, lowercase here, will be the coupling coefficient. And it is a unitless quantity. And typically speaking, when 0 is less than K, sorry, that looks too much like a capital K for my taste, is less than 1/2, we have loosely coupled coils. When K is between 1/2 and 1, we have tightly coupled coils. And when K is exactly equal to 1, we have perfectly coupled coils. In a practical sense, no. You can get very, very close. So let's talk about what might influence the value of K. Okay.
This is a question. In most cases, with Python, that form.
That you can get in a practical sense, absolutely yes. So the value of K is dependent on a number of different things. Okay, it's dependent on the physical geometry of the system, as well as the core material. So if we look at the solenoidal transformer on the left, that would probably have K value of less than 1/2, because there is a huge air gap in what I'm going to call the magnetic circuit that would represent this device. Now, we're not going to talk about magnetic circuits in any formal form until we get into your second power class, which you guys will have next winter. Yes, Brock. The solenoidal one on the left. Yes. So let me explain why. We have our magnetic field lines going up like so, and then they're going to hit this air gap and wrap around like so. And the presence of that air gap gives our magnetic flux place to spread and effectively to lose energy. So those coils are going to have a significant amount of losses. And it also depends on what the core material is made of. So from a purely geometric standpoint, this one's typically going to have a lower K. If we look at our transformer over here on the right with this rectangular core, we're going to have something like this as our flux path, where we are assuming that our core is made of a material with a very, very high permeability. So permeability is a material constant, and it's related to how easily a material can be magnetized. So certain materials like iron can be magnetized extremely easily. And so if we have an uninterrupted core like this, so there is no air gap or anything like that, that high permeability material is effectively going to make sure that all of our magnetic flux stays in that region. Practically none of it spreads out. And so we have very, very high coupling between the coils. There are a couple of other things that we have to do to make sure that we don't have losses in the system, called laminating the core and all that kind of good stuff, but we'll get into that in our next class meeting. Effectively, because the material is conductive, we can induce what are called eddy currents. Eddy currents develop a magnetic field that is opposing the changing flux that's passing through. And so by laminating the core or cutting it into very thin strips, separated by very thin insulating materials, we can make sure that the eddy currents that are induced in the core are very, very small and therefore don't oppose the flux, so that our losses are minimized. But again, that's a problem for the next class, where we get into the nitty-gritty of how these things are made and how they practically perform, and all kinds of gross things like nonlinear magnetization curves and all that kind of good stuff. Right. All right. The introduction of an air gap or something like that can also cause the coupling to be lower. So for instance, just as a sake of argument here, if I were to cut out this notch like so, I would still have a transformer effectively, but now my coupling wouldn't be quite as good because I have that one region where I allow my field to kind of spread out and things. Now you may be thinking to yourself, well, why would you ever want to do that? Sometimes you're physically required to. It's hard to wrap things around a solid structure like this. And then in other things, like I know this is getting ahead of myself, but we're going to find out in our next class meeting that an induction motor is nothing more than a transformer where we allow the secondary coil to rotate. We literally have to have air gaps in order to allow that rotation to occur. So, so in a practical sense, the best we can ever get is a tightly coupled coil, but that can be K values of 0.99 or thereabouts. So we can get extremely close to perfectly coupled coils if we use incredibly high permeability materials.
So whenever you have off heat, or does it just like so that
Heat. Yes. So that's, well, technically the answer to your question is both of the above. So there are going to be ohmic losses where energy is converted into heat. Again, beyond the scope of this class, but what we're going to start talking about in 360. So it takes energy in order to align the magnetic domains of high permeability materials. Some of that is going to manifest itself as heat. Some of that is effectively going to be like residual stored energy in the system, which is how we get permanent magnets and all of that kind of good stuff. So there are several different loss mechanisms that we are going to talk about in our later classes in great detail. So I'm going to answer this question and then we're going to move along because I don't want to derail this thing. Okay, so certain materials, let's say that you pulled a chunk of iron out of the earth, okay? Would that be a magnet? No, it wouldn't be. It 100% raw iron material would not be magnetic. It would exhibit some magnetic properties on the very, like the micro scale, but all of the magnetic domains would be randomly oriented, okay? So that all of our magnetic, internal magnetic fields would be randomly oriented, so they're just as likely to cancel each other out as anything, okay? When you wrap a wire around a piece of, so like a rod or something like that made out of iron, what's going to happen is when you pass a current through that, the external magnetic field is going to cause all of the internal magnetic domains to that rod to align with the applied external field. When you take that external field away by turning off the current, there is what's called residual magnetization. So that iron material effectively has a memory of the amount of, or the direction of the field lines that were in it previously. And so it will hold that. It takes you applying a current in the opposite direction, and depending on the type of material and a couple of other things, maybe a significant amount of current in order to fully demagnetize the material. So permanent magnets are actually made with electromagnets. It's just their material properties that allow them to hold on to magnetization even after the current is taken away. So that's why if you wrap a wire around some types of nails, like I think galvanized steel probably works. Don't quote me on that one, but I know that you can wrap a wire around certain types of nails and all that kind of stuff, pass a current through it, and then that nail becomes magnetic because you just made your own electromagnet and magnetize the core so that it will have some residual magnetization. For what it's worth, this concept of residual magnetization and all of that kind of stuff is how all computer storage worked up until the last, what, 15 years-ish, Ron? When we got away from magnetic hard drives and all that kind of stuff and started working with solid state drives. You guys are probably too young for this, but tape media, like cassette tapes and all that kind of stuff, are the exact same thing. Yeah. So you have some idea of what a cassette tape or a VHS is and all that kind of stuff? Okay.
Figure yourself. I remember more car myself watching VHS.
All right, anyway, so now that we've talked about magnetization and you guys all are figuring out how old I am, let's move along to a mathematical description of our coupling coefficient K. So mathematically, our coupling coefficient K is the ratio of our mutual inductance M divided by the square root of L1 and L2, where L1 and L2 represent the inductance, the self-inductance of coil 1 and coil 2. So we could rearrange this in order to find that our mutual inductance M is nothing more than our coupling coefficient K times the square root of L1 times L2. And from here, if K is equal to 1 specifically, we find that our mutual inductance is simply the square root of L1 times L2. Right. So self-inductance is all about flux generated by a particular coil passing through that same coil. Mutual inductance is flux generated by one coil passing through a second coil. So it is impossible for us to have a mutual inductance without two coils closely placed together so that the flux generated by one passes through the other. And these transformers are specific circuits designed to force that to happen. Without magnetic coupling or coupling between the coils, transformer wouldn't do its principal function, which we'll get to in a little bit. Go for it. So it depends on whether or not it has a single coil or two coils. If it is a single coil, that is what's known as a toroidal inductor. If it has multiple coils, meaning that you have two sets of wires leading, actually two or more, because we can definitely have transformers with multiple outputs effectively, as you will, those would be considered transformers. So required to have at least two coils in order for it to be a transformer because it needs to have magnetic coupling between the coils. So, yep, so if you crack open really any electronic device and all of that kind of stuff, you might see a ceramic ring with a wire wrapped around it. Sometimes that wire is it's got enamel on it and all of that kind of stuff. Other times it won't, just depends. Size of the wire depends, all of that kind of good stuff on the amount of current that you're needing to pass through and transform. But anyway, if it's a single wire, it's an inductor. And if it's multiple wires wrapped around it, it's a transformer. All right. So in addition to the two coupled coils, a realistic transformer circuit also includes some resistances that are used to account for the ohmic or heat losses in the coil. So a more realistic transformer circuit might look something like this. So in the frequency domain, we would have some source voltage applied to terminals A and B, like so. And then we would have some resistance R1 representing the AC resistance of the wire that's used to make the winding of our coil L1. That AC resistance is typically a little bit larger than the DC resistance that you would measure with a multimeter or something like that. There is an equation to determine it. I believe it's something in the ballpark of just 1.6 times the DC resistance, but don't quote me on that. It's been a minute since I looked at it. And then over here on the right-hand side, we'll have our second coil. Some resistance R2, representing the AC resistance of our second coil. I'm going to call this terminal C and D, and then attached to C and D, we might have some arbitrary load impedance ZL, and I'm going to specifically indicate my mutual inductance here. So you might see this either given as a mutual inductance M or a coupling coefficient K, and if you know what L1 and L2 are, if you have M, you can find K. If you have K, you can find M. So generally speaking, one coil and its associated resistance is called the primary side of a transformer, and the other coil and its associated resistance is called the secondary side of a transformer. And there's really nothing physical about the system that is preventing the primary from acting as the secondary or vice versa. It is literally typically whichever side is connected to the source you consider to be the primary, whichever side is connected to the load you take as the secondary. So we can use this and the relationships that we have previously developed to kind of refer all of the stuff that's connected on the secondary windings over to the primary windings to find an equivalent impedance. So the impedance Zn, let me draw a current here. So let's say that this is the current I1, and this is the voltage V1. So that's the voltage drop across the primary windings, the terminals of the primary windings, and the current flowing into the terminals of the primary windings. We can define an input impedance, Zn, as simply the ratio of V1 to I1, right? So whatever that voltage is divided by whatever that current is gives us the impedance that is, in this case, seen by our voltage source. So I want us to kind of play around with that a little bit, okay? So let's define some mesh currents. I'm going to call this mesh current I1 like so that it represents exactly the same I1 that I described as flowing into the primary terminals. And I'm also going to define a mesh current I2 like so. And I'm drawing it in this opposite direction so that it flows into the dotted terminals. So that when we do our math here, we're just going to get plus signs and all of that kind of good stuff. So if we were to apply Kirchhoff's voltage law at our primary windings, we would wind up getting the relationship negative Vs plus R1 plus J omega L1. Make sure that corner is good. Times our current I1 plus J omega M times I2. So the current R1 sees a current of the resistance R1 sees a current of I1. The impedance L1 sees a current of I1. Because that current is flowing into the dotted terminal, that's why we have a plus sign on that term. Then we have our mutual inductance term, and because the current I2 is flowing into the dotted terminal, once again, we have a plus sign on the mutual inductance term. We can now write a KVL expression at our secondary. And we would have R2 plus J omega L2 plus whatever our load impedance ZL is times I2 plus J omega M times I1 is equal to 0. And this could be rearranged to find that our current I2 is nothing more than negative J omega M divided by R2 plus J omega L2 plus ZL times I1. If we substitute this relationship for I2 into our KVL equation at our primary and rearrange, what we wind up getting is Vs is equal to R1 plus J omega L1 times I1, bless you, plus J omega M times negative J omega M divided by R2 plus J omega L2 plus ZL. What is J times negative J, or negative J squared? I should know this. So, what's J? Tell me what the imaginary number is. What is J? Square root of -1. Square that. -1, a square root of -1 times the square root of -1 is just -1. What's negative times -1? +1. So negative J squared is and always will be +1. So that allows me to write this as omega M squared in the numerator, positive, divided by R2 plus J omega L2 plus ZL. And from this, times I1, which I missed earlier. And from this, our input impedance is just going to be Vs over I1, which is the same thing as V1 over I1, is R plus J omega L1 plus omega M squared over R2 plus J omega L2 plus ZL. So that's the result that we got for this particular circuit, but I want to point something out here. Sorry, and this should be an R1. What does this bit here, R1 plus J omega L1, represent? Let's scroll back to our circuit. Exactly right. So that is the impedance of the primary, 100%. So we're going to call this the primary loop impedance. Now we have this bit right here. Let's look at the denominator specifically. R2 plus J omega L2 plus ZL. That is the secondary impedance. And then that factor of omega M squared is us reflecting that impedance from the secondary to the primary. We'll go into that in greater detail once we learn about ideal transformers and all of that kind of stuff. So we're going to call this bit right here the reflected secondary loop impedance. So yes. Nope. We divided through by all of the I1s to only have an impedance. So using this concept of an input impedance, we can actually eliminate the need to set up a system of equations to solve for mesh currents, at least in simple circuits like this. Okay. So let's work a quick example here. In IN, this Z right here, it is indeed. Scrolling back up, this entire time, we have been trying to define the input impedance seen by looking into the primary terminals of a transformer. All right, so let's say that we have the following frequency domain circuit. We have a 120 angle 30 degrees volt source. Connected to terminals A and B. Here we have a 3 ohm resistance, sorry. And also a minus J2 ohm capacitance. And then a J5 ohm coil impedance. Dot on the top left. Here we've got a J20 ohm impedance. Dot on the bottom. And C. D like so. And let's make our load simply a 4 ohm resistor. I'm going to define two mesh currents. Once again, I'm defining the mesh currents in such a way that they flow into the dotted terminals. And what I want us to find is the value of our mesh currents I1 and I2. We're going to do this without setting up systems of equations and all of that kind of jazz like we did earlier. Or at least we're going to do this in a way that doesn't require us to use a computer in order to solve any equations that we get. Okay. So how can I find the input impedance for this system? I'm going to what's the primary loop impedance? Oh, and also I need to define my mutual inductance. My apologies there, J2 ohm. So what's my primary loop impedance in total? So what's the real part? What's the imaginary part? Positive or negative? Yep, so plus J3 ohms. Okay, so there's my primary loop impedance. We all okay with that? I firmly agree that positive J5 minus J2 is positive J3. So I'm good with that. What's the impedance of my secondary loop? Not worried about reflected yet, just the straight up impedance of the secondary loop. So what's the real part? 10. 6 plus 4 is equal to 10. Plus J16 ohms. All right. So in the numerator here, we effectively just need the magnitude of the impedance of our mutual inductance, right? So we don't worry about the J, it's just whatever omega M was, and then we square that. So what would be the omega M part of our mutual inductance? So not the J, just the 2 ohms. If we throw this into our calculators, what we should find is that we get an impedance of 3.112 plus J 2.820 ohms. So this is the input impedance seen typically speaking, I like to express impedances in rectangular form, voltage and currents in polar form. But it's 4.2 angle 42.181 degrees ohms in polar form. I also happen to have that one written down. All right, so knowing what our input impedance is lets us calculate a numerical value for the mesh current I1, right? So I1, somebody tell me what it should be. You're doing too much work. Ohm's law. So V over Z in this case, but yes. So 120 angle 30 degrees volts divided by that input impedance of 3.112 plus J 2.820 ohms gives us 28.571 with an angle of negative 12.181 degrees amps. Is it the same as I2? It is not. So we're about to solve for I2. So let's talk about how we can solve for I2. Okay. There are two different ways to approach this, but I'm going to do it the laziest way possible because I'm me. Okay. Not really. So I'm going to write a KVL equation around mesh one. Okay. So this is what you were trying to do a moment ago.
Yeah.
So now do it.
Okay, so we can-
I1 because that's the current flowing around that loop. And then we have our mutual inductance term. Is equal to 0, which means I2 is nothing more than positive 120 angle 30 degrees volts minus 3 ohms plus J3 ohms times I1, which we know to be 28.571 angle negative 12.181 amps. And all of that gets divided by J2 ohms. J5 minus J2 is positive J3. And there we get 3.029 with an angle of negative 160.176 degrees amps. So I want you guys to take a moment and look at problem 1 of the in-class assignment. So problem 1 is incredibly similar to what we just did. So I want you guys to walk me through it instead of the other way around. So I'll give you some hints. I can observe just by looking at this that our original circuit is in the time domain, and we should hopefully all know that we will never work a circuit in the time domain in this class. So what should our very first step be? Convert it into the frequency domain, okay? So how am I going to convert this source voltage of 50 cosine 2000t into a phasor voltage? 50 angle 0. All right, so I'm going to put that up here. We all know that our resistor values stay the same, so I'm not going to mess with those. So you are correct that omega is equal to 2000. So please use that and tell me what my 25 microfarad capacitor will look like in the frequency domain. Anna, I'm going to ask you to do that calculation because you're watching TikToks or some shit on your phone. So what's the equation for the impedance of a capacitor? Yeah, for any circuit where we're having sinusoidal steady state excitation. Impedance of a capacitor. We've been having to do this for okay, so maybe ask somebody at your table. Let's phone a friend. Let's put it in the parlance of Who Wants to Be a Millionaire or whatever.
I just,
So apparently I'm being incredibly intimidating. That's okay. I'm okay with that.
oh, it's just a conversion, -1 over J omega J.
So you're mixing them all together. Let's try this again.
Is that inductor? That's inductor.
So for a capacitor, it is 1 over J omega C, which is the same thing as negative J over omega C. So either way, 1 over J omega C, put it in your calculator, tell me what you get. Still talking to you, Adam.
Oh, yeah.
Yes, 2000 is the angular frequency omega. So somebody tell me what the 25 microfarad capacitor is going to look like. So I'm hearing negative J20. Let's see. All right. Sure. So do the other capacitor since that's fresh on your mind. Negative J50, thank you. All right, now let's take care of our inductors. So how do I convert the 3 millihenry inductor into its impedance? J omega L. So somebody tell me what that's going to be. J6, all righty. And what about the 10 millihenry inductor? All righty, and lastly, our 1 millihenry of mutual inductance. Yep. All right. So we have converted our circuit from the time domain into the frequency domain, or at least we will once I calculate this V out right here. Yeah. All right. So the first part of this question is asking us simply to determine the input impedance seen by the voltage source. So this is literally the exact same thing we just did on the last example problem. So I want you guys to tell me how to do it. All right, so that is our primary impedance. 2 ohms squared in the numerator. All right, what's my denominator going to look like? Okay. It should not. Negative j times positive j is equal to positive 1. All right. So if we throw this into our calculators, we should get 10.059 minus j 13.965 ohms. The second part of our problem asks us to determine the output voltage of our circuit. Okay, so this is where things are kind of different from what we did previously. Okay. So I, to this point, have not defined any mesh currents or anything like that. So I'm going to go ahead and do that now. I'm going to say that this is my mesh current I1, choosing it in this particular direction, just so that V divided by Z gives me my mesh current I1. And I'm going to choose this mesh current I2 in this direction, so that V out is nothing more than whatever 50 ohms times I2 is. Sure. All right. So how do I find I1? I literally just told you a moment ago. Too much work. Ohm's law. So I get this to be 2.905 minus, sorry, getting my answers to different parts mixed up. My apologies. 54.235 degrees. Goodness, I can't write today. Amps. All right, so now do what your inclination is to do that. Okay. Okay. What? KVL around mesh 1. Okay, so I'm putting it as positive 50 ohms and I'm just moving it to the other side of the equal sign already. So is equal to, all right, so now hit me with what's what. Okay. Okay. So I'm gonna do the 10 ohms minus the J20 ohms for sure. Okay. So that's these two together. And now I need to pay attention to things because my current is flowing into the undotted terminal of my coil. So I have to pay pretty strict attention, right? So if I want that term to have a positive sign, I effectively have to define my voltage to have the positive polarity terminal at the undotted terminal because the current is flowing into the undotted terminal, right? So if the positive polarity terminal is at the undotted terminal and the current is flowing into the undotted terminal, then I will get plus J6 ohms times I1. What's my mutual term going to look like? No, so just to be really clear here, it will be positive. The positive polarity voltage of V1 is at the undotted terminal of coil 1, and the current I2 is flowing into the undotted terminal of coil 2. So that sign has nothing to do with the polarity of the voltage across coil 2. So don't need it, and in fact, actually, we will never need it for this problem at all. Yep. Yep. So we have this expression that lets us find I2, right? So I2 is going to be 50 angle 0 degrees volts minus 10 ohms minus J. So I'm going to add this minus J20 I1 and plus J6 I1 together to give me minus J14 ohms. I1 is 2.905 angle 54.235 degrees amps. Yeah. Divide all of that by J2 ohms. And we should get I2 comes out to be 0.100 with an angle of negative 4.802 degrees amps. Yep, just because that's what the mutual inductance happened to be. From here, V out is nothing more than 50 ohms times I2, which I got to be 4.982. So this is without any rounding error. It would be literally just 5 if we introduced rounding error. Angle negative 4.802 degrees volts. And from this, our time domain voltage V out of T would be 4.982 cosine 2000 T minus 4.802 degrees. Oops, volts should go on the outside there. So for a relatively simple circuit like this, wherein we have some fixed impedance on the primary side and some fixed impedance on the secondary side, we no longer need a computer in order to determine what our mesh currents are or what any possible voltage is. All right. So now let's talk about T and pi equivalent circuits. All right, actually, I'm going to move this on to the next page. I'm not going to have enough room. Oh, well, that's annoying me. Screw it, I'm just rewriting it. It's pissing me off at this point. All right. Not going to derive this because that would bore you guys to tears. Instead, I'm just going to hit you with our relationships, okay? So I'm going to put a transformer over here on the left-hand side, wherein I'm going to define different parts here. Do what?
What's the word?
Equivalent circuits. Yes, so it is not an equation. We will use equations for sure. So let's say that I have a simple transformer like so. Oops. We're going to start with dots on the same side. This is my voltage V1 across my primary. This is my voltage V2 across my secondary. And I'm going to draw current I1 such that it flows into the dot, and current I2 such that it flows into the dot. I'm going to call this terminal A, B, C, and D. And what I'm going to do is I'm going to draw some dashes here as if B and D were physically connected together. They will not be in an actual transformer. I mean, they could be if we forced it to happen. But generally speaking, the primary side and the secondary side are electrically isolated. But this is going to give us one of our terminals of our equivalent, okay? So our first equivalent circuit, I'm going to draw up here to the top right, okay? So here's A, here's B, I'm going to call this inductance Lx. This inductance Ly. Here's terminal C. And this inductance down the middle, Lz, like so. And now over here, I have terminal D. So this is one of our equivalent circuits. We're going to define things here in a moment. So this is what we're going to call our T equivalent circuit, because if we condense that long line for B and D down to just a single node point, it would look like the letter T, and engineers are lazy. So let's specify some things here. First of which, the voltage V1 will still just be the voltage drop across terminals A and B. Voltage V2 will still just be the voltage drop across terminals C and D. The current I1 is still the current flowing into terminal A. The current I2 is still just the current flowing into terminal C. So now let's define these inductances LX, LY, and LZ in terms of L1, L2, and M from our original transformer circuit, okay? So LX is nothing more than L1 minus M. Ly is L2 minus M, and Lz is just M. So that is our T equivalent circuit and how we get the different parameters of that equivalent circuit. Okay. Now I want to be clear here. These definitions, Lx is equal to L1 minus M, Ly is equal to L2 minus M, and Lz is equal to M, is dependent on us having the dots on the same side and the currents flowing into the dots. If those conditions are not met, it's going to change those relationships. I'll tell you how to do that in a moment. Our second alternative is what's called a pi equivalent circuit because it kind of looks like children's letter pi. So once again, I'm going to have my set of terminals. So here's A and B. And now between A and B, I'm going to have an inductance LB between what are effectively A and C. I will have an inductance LC. Here's my C terminal. Down here, I will have an inductance LA. Here's my D terminal, like so. Just as a heads up here. What is that thing on the top for my zero? See, what if I made LX and LY kind of slant up like this? This is exactly the same thing as the Y delta transformation. Literally, exactly the same thing as what we just did. Here is our voltage V1, our voltage V2, the current I1, and our current I2. And because these expressions are a little bit longer, I'll put them down below. So LA is L1, L2 minus M squared divided by L1 minus M. LB comes out to be L1, L2 minus m squared divided by L2 minus m. And lastly, LC comes out to be L1, L2 minus m squared divided by just m. All right. So actually, let me do this in red. So we'll bring it to your attention. If one, putting this in capital letters and underlining it to bring it to your attention, of the currents is flowing into an undotted terminal or if the dots are on opposite sides, replace m with negative m. That's it.
Current is flowing into, what are those two really?
An undotted terminal. So effectively, if I change the direction of one of the currents, or I put the dots on opposite sides, everywhere you see m, replace it with negative m. So let's put that into practice. Let's look at in-class assignment problem 2. So we have this network right here, and I'm specifically asking you to use a T equivalent circuit to determine the impedance seen between terminals A and B of this network. So here's A, here's B. Our 8 ohm resistor remains unchanged. Our minus J3 ohm capacitance remains unchanged. Because we are replacing this transformer right here with an equivalent circuit, I'm going to make a couple of notes here. I'm going to call this point right here terminal A. This guy down here will be B. This point right here is terminal C. And this guy down here is effectively D. B and D are literally tied together with a short circuit in our model, so I'm just going to treat it as one point. So here's where A is going to be. Here's where C is going to be. Here is where B/D is going to be. We'll transform our transformer in a moment, but I'm just going to connect the rest of the stuff really quickly. So here's my minus J5 ohm. Here's my 4 ohm. Here's my 15 ohm. And now, because I'm explicitly told to use a T equivalent circuit, there's my T equivalent circuit right there in the middle. and I need you guys to tell me what impedances should go there. All right. So this guy right here is playing the role of Lx, this guy is playing the role of Ly, and this guy is playing the role of Lz, based on where it's connected between the terminals that I have defined. Notice that our dots are on opposite sides. Nowhere is any current defined, so we are not going to worry about that part. So since the dots are on opposite sides, all I do is apply the equations that I gave you, except everywhere that you see m, replace it with negative m. So what should Lx be? L1 plus m. So what's L1? J6. What's m? Add those together. J9. Okay. What's Ly going to be? Yeah, L2 plus m, which is just J9 plus J3, or J12. What is Lz going to be? Negative m. So negative J3 ohms. All right. So let's go a step further. And now let's just lump stuff together like this was a regular old circuit, because that's exactly what it is. So to me, it looks like I have 8 ohms in series with minus J3 ohms in series with J9 ohms. So I'm going to lump those together and call that 8 plus J6 ohms. My middle branch, I have 4 ohms in series with minus J3 ohms. So I'm just going to put this as 4 minus J3 ohms. And my right-hand branch, I have 15 ohms in series with J12 in series with minus J5. So to me, that looks like 15 plus J7. So what would my equivalent impedance for this be? Mm-hmm. So that 4 minus J3 ohms in parallel with 15 plus J7 ohms, and you guys can throw that into a calculator just as well as I can. Okay. So anything particularly wild or crazy about that? So let's see how we might use an equivalent circuit to aid us in a circuit analysis problem. So what if I gave you something like this? So I have a circuit containing a transformer, and my ultimate goal here is to solve for the voltage V out. And I believe that we can use our equivalent circuit model for our transformer in such a way that we actually won't need to solve for any, or we won't have to solve a system of equations in order to figure out what this voltage V out is. Okay. So I'm going to redraw this circuit now. And we're going to do the exact same thing that we did a moment ago, where we're going to replace our transformer with its T equivalent circuit and see what shakes out of that. So that might look something like this. So let's see here. This 4 ohm is going to stay the same. This minus J2 ohm is going to stay the same. This 10 ohms down here will stay the same. This 20 ohms right here will stay the same. Here's V out. So this inductance on the top left, what's it going to be? Disagree. So it is LX effectively, but what is it going to be? The dots are on the same side. J2. So J6 minus J4 is equal to J2 ohms. Absolutely. What about this guy over here? J8 minus J4 is equal to J4 ohms. Remember, dots are on the same side, so we have L minus M. What about this guy down here, which is playing the role of LZ? Positive J4, because we don't need to change the sign because the dots are on the same side. So we now have this thing, and our ultimate goal is to figure out what V out is. To me, this looks effectively exactly the same as the circuits that we were dealing with way back in the first part of this class. So there are a number of different ways that we could solve this. I'm going to solve it exactly how I did stuff like this way back at the beginning of the class. I'm going to call this voltage Vx, and I'm going to treat this thing right here as if it's ground. And so what I would have, applying KCL at node X, I would have Vx minus 50 angle 0 degrees volts divided by 4 ohms, because my minus J2 and my plus J2 cancel each other out, plus Vx divided by 10 plus J4 ohms, plus Vx divided by, sorry, that 20 looks crappy, 20 plus J4 ohms is equal to 0. So I would have Vx over, times 1 over 4 ohms plus 1 over 10 plus J4 ohms plus 1 over 20 plus J4 ohms is equal to 50 angle 0 degrees volts over 4 ohms. We'll grab a calculator real quick. Solving this differently than I did previously. From this, I got Vx is equal to 32.316 with an angle of 6.546 degrees volts. Now, how would I solve for V out? Knowing what Vx is. Voltage division, sure. So V out would just be Vx times 20 ohms divided by 20 plus J4 ohms. 31.688 with an angle of negative 4.764 degrees. So our transformer equivalent circuit, let us break this down into something that we could have solved on like the third day of this class. So it can be an extremely powerful tool in our circuit analysis. All right. The last thing that I want to cover with you guys today is energy stored in a transformer. P is usually going to be the easier thing to use, yeah, because it just fits so nicely with most things. Now, if we had, I'm sure I'll give you a homework problem that's just going to force you to practice with the pi, but realistically, you're going to use the P most of the time because it's easier to deal with. All right. And as it turns out, we're actually going to use the T equivalent circuit here in the energy derivation. All right. So let's say that I have a simple transformer. Like so, where here's L1. Here's I1 of T. Here's L2. I2 of T. Like so, when we have some mutual inductance between these two. If we were to replace our transformer with a T equivalent circuit model, we would have something like this. So I'm representing this as L1 minus M because the dots are on the same side and the currents are flowing into the dots. This would be L2 minus M for the exact same reason. And this would be M, like so. So our current I1 is still the current flowing into the primary side. Our current I2 is the current flowing into the secondary side. I want one of you guys to tell me what the current flowing through that central inductance M is going to be. Yeah, just Kirchhoff's current law, absolutely right. So if I1 is flowing in and I2 is flowing in, then the current flowing out is I1 plus I2. So the energy stored in our system is just going to be the energy stored in inductance Lx as a function of time, plus the energy stored in inductance Ly as a function of time, plus the energy stored in inductance LZ as a function of time. So I'm saying it's just the sum of this guy plus this guy plus this guy added together is the total energy stored in the transformer. And because our T equivalent circuit is electrically equivalent, it must be the same thing as the total energy stored in our original transformer. So, any of you guys remember what the equation for energy stored in an inductor is? 1/2 Li squared, that ring any bells? Ron's smiling like it should. All right, so 1/2 Lx times I1 squared plus 1/2 Ly times I2 squared plus 1/2 Lz times I1 plus I2 quantity squared. And now we're going to substitute in for Lx, Ly, and Lz. Yes, thank you. That is correct. 1/2 L times the current squared. That is the generic expression for the energy stored in an inductor. We have 3 inductors, 3 different currents. Yes. So this is going to look like 1/2 L1 minus M times I1 squared plus 1/2 L2 minus M times I2 squared plus 1/2 M. So I'm going to have I1 squared plus twice I1 I2 plus I2 squared, like so. That's just I1 times I1 plus I1 times I2 plus I2 times I1 plus I2 times I2. Just boiling it out, 8th grade math style. All right, so now let's kind of split things up here a little bit. Okay. So I have 1/2 L1 I1 squared minus 1/2 M I1 squared plus 1/2 L2 I2 squared minus 1/2 M I2 squared. And I'm continuing that same expression down here on the second row because it's too large. 1/2 M I1 squared plus twice M I1 I2 plus 1/2 M I2 squared. So I have a negative 1/2 M I1 squared here and a positive 1/2 M I1 squared here. So that guy goes away. You know what? You are 1/2 times 2 is definitely 1. So thank you for that. I was about to come to that realization myself. Thank you, though. We have negative 1/2 M I2 squared and positive 1/2 m I2 squared. So those guys cancel each other out. And so what we wind up left with is just 1/2 L1 I1 squared plus 1/2 L2 I2 squared plus m times I1 times I2. And now I'm going to put another note here because once again, this was derived under the very specific instance where dots are on the same side, currents are flowing in. So if either current is reversed or the dots are on opposite sides, replace m with negative m. All right, so let's look at in-class assignment problem 3, and then we'll be done because we're out of time. We probably will only have an opportunity actually to work part A, so I'll leave you guys with part B. Okay. So currents in the network shown are given as I1 is equal to blah, blah, blah. I2 is equal to different blah, blah, blah. And we're asked to determine the total energy stored by the transformer in network A at T is equal to 1 millisecond. And then in part B, which I don't think we'll get to, the total energy stored by the transformer in network B at T is equal to 1 millisecond. So let's start with some low-hanging fruit. What's L1? 2 henries. Great. What's L2? 1 henry. What's M? Go way back to what we did the very first thing in class, because I gave you K, and we need to calculate K based on, excuse me, we need to calculate M based on K, L1, and L2. So K times the square root of L1, L2, if I'm not mistaken. So that would be 0.6 times the square root of 2. Or 0.846 henries. Okay. So here we have I1 and here we have I2. We're trying to find things at a specific time of 1 millisecond. So I1 at 1 millisecond means I'm literally just going to plug 1 millisecond into this equation. Excuse me. So 8 times the cosine of 377 times 0.001 minus, now I got to pay a little bit of attention here. So I'm going to write this out. So I have 8 cosine 377 radians per second times a time of 0.001 seconds. That's just me converting 1 millisecond into seconds. Minus 20 degrees. Okay. I'm going to move this over here. When I multiply 377 radians per second times 0.001 seconds, what unit am I going to get? Radian. Is a radian the same thing as a degree? No, so I need to convert either radians into degrees or degrees into radians. I'm going to convert radians into degrees by multiplying by 180 over pi. So I get I1 at 1 millisecond to be 7.997 milliamps. I2 at 1 millisecond, I'm going to do a similar thing here. So 4 times the cosine of 377 times 0.001 times 180 over pi minus 50 gives me 3.519. And now I have literally every different thing that I plug into my equation. Right? We go back to our engineering paper thingy here. We have L1, we have I1, we have L2, we have I2, we have M, we have I1, we have I2. Literally just plug the numbers into the equation. One thing I want to note, either current is reversed or the dots are on opposite sides. So let's look at things here. So I2 is reversed. Oh, sorry. So we need to replace everywhere we had M with negative M. That's it. Just really quickly here, for part B, a current is reversed and the dots are on opposite sides. So what would we do? We would not change our equation at all. That's correct. Yep. So if the current is in the opposite direction and the dots are on opposite sides, we don't need to make any changes. Was it? All right. So like I said, we actually covered 2 lectures worth of material today. We are not having class on Thursday so that I can mentally prepare myself for Friday.